Assalamualaikum and good morning, everyone. Welcome back. So now we are going to proceed with our next session, non-parametric tests. So please welcome Prof. Azmi.
Okay, thank you, Fitri, our chairperson for today. Okay. So right now, everything looks a bit different because I still have the wrong background. Okay, allow me to change the slide. Of all the lectures, this is the worst lecture. Usually what I do last time, whenever I'm asked to give this topic, I will tai chi this to someone else. But I think they knew my trick already. So now everybody refused to take over this slot. So it has come back to me. Okay. So I'm going to change the slide now. Wow, MMA came out already. Oh, that's very nice. Ayo. Can you cancel it out just now? Okay. Okay. Gelak kan dia. It's a tease. Suka mengusik. Alright. So right now we are going to go back to the slot. Okay. How I can pull this thing off? I use a special software. They call it OBS Studio. So this software, OBS Studio, allows me to merge the PowerPoint and the video together. So that's why you can see this, me and the PowerPoint together. At my back is a green screen. Dekat belakang saya adalah screen hijau. So allow me to show you how it looks like. Okay. So there's the green screen. So you can see that behind me is the green screen. So once I enable what you call the chroma key, the green screen changes, and you get my video and the PowerPoint together. Okay. So how much does it cost to get a green screen? It is only 20 ringgit on Lazada. You can check it out. But of course, for the faculty, takkan nak beli yang 20 ringgit kan. So we ask for a green screen yang harga 1,500. Best sikit, mahal kan, beli barang mahal kan. Alright, so the nice thing about this green screen, it is portable and we can dismantle it and bring it around. So we can use it at the bilik tali sidang, we can use it inside the auditorium, so on and so forth. Okay, I'm going to share my screen now. Okay. The reason why you're not seeing much difference is because my video was already spotlighted. That's why you saw the same one. What's the advantage of me sharing the screen? Hopefully the words are clearer when I share the screen. Okay. All right. I need to shift this thing aside first. Otherwise I cannot see the PowerPoint. Okay. So when we talk about non-parametric analysis, non-parametric is the other version of of a statistical test. So what we have covered from Friday until today are all the parametric tests. So when we talk about student-C test, that is a parametric test. When we talk about Pearson correlation, that is a parametric test. When we talk about PET test, that is a parametric test. So for every one of the parametric tests, there is a non-parametric equivalent. For every parametric test that we have a non-parametric equivalent. Okay. So for the non-parametric equivalent is the Wilcoxon test and the Kruskal-Wallis test. Okay. So if you remember back when we had the lecture last Friday, we talked about data exploration. We talked about testing for the distribution. Okay. We talked about screening for errors and correct them. Okay. And if the data is not normal, you cannot use parametric analysis. You can use non-parametric analysis. Okay. So now I'm going to cover the non-parametric analysis. Okay. So as mentioned earlier, there are so many statistical tests. Your biggest problem is to decide which one is the appropriate statistical test. Okay, which one is the appropriate statistical test? So how you decide which one is the appropriate one? You have to look at the number of the observations available inside there. Okay, you have to look at the number, how many independent groups you have, how many dependent groups you have, the type of data, whether it's continuous or categorical. Okay, I know the word to use is quantitative and qualitative, but the word quantitative and qualitative does not sound so different. So I rather use the word numerical and categorical, because numerical numbers, categorical categories, quite clear. Then we look at the data, whether it's normally distributed or not, and of course we look at the objective analysis. So why we do non-parametric? We mentioned already, if your data is not normally distributed, you can only do non-parametric analysis. Okay, so one example is the Wilcoxon Rank Sum test. As mentioned here, it is based on analysis of ranks. Okay, so who end up having to do this non-parametric analysis? Usually people who do animal studies. People who do animal studies. Why? Your sample is very small, 9 rats, ataupun 9 guinea pigs, so forth. So very few. So you have to do non-parametric analysis. Okay. So what are the non-parametric analysis? One is Fisher exact test, which we already covered last Friday. Okay. Then we have the Wilcoxon Rank Sum test. We have the Kruskal-Wallis one-way ANOVA test. We have the Wilcoxon sign rank test. For the Spearman and Kendall rank correlation, we touched a bit earlier when we were doing the Pearson correlations now. Okay. So now what's left is only the Wilcoxon rank sum test, and Wilcoxon sign rank test, and the Kruskal-Wallis. Those are the only analysis that we're going to cover now, because the rest has been covered earlier. Okay, what's the advantage of using non-parametric tests? Last time, before the age of computer, it is easier to calculate. Why? So because when you do manual calculation, and there's no need for you to calculate the mean, there's no need to calculate the standard deviation. You just arrange the numbers, then you sum up the ranks, then you get the p-value. So very easy. Okay, it is very easy. But if your data already started, you already have all the data in continuous nature. For example, the data you have the BMI. You already have the BMI. And then suddenly you want to decide to analyze using overweight and normal. You must have a good reason for that. If there's a good reason, then you can go ahead and do that. But otherwise, better to keep the data in its original form, which is the numeric data. Okay. Just take note, non-parametric test is only suitable for small data set. Most of the tables are maximum number of n, number of samples is only for 30 or less. So if your samples are larger than 30, the tables are not widely available, so it is very hard to calculate manually. Can you calculate the non-parametric test using SPSS? Can, but not much to discuss. They just give you the Z value or the P value. So there's nothing to discuss, absolutely nothing to discuss. Okay, so let's start with the first one. Okay, the first one is a Mann-Whitney U test, also known as the Wilcoxon Rank Sum test. So last time they call it Wilcoxon Rank Sum test, but because when we say the Wilcoxon test, people confuse whether it is for Wilcoxon Rank Sum test or Wilcoxon Sign Rank test. So they came up with the other name of Mann-Whitney U test. Basically, Frank Wilcoxon is from UK. Mann and Whitney, they are from the East Coast and West Coast of America. Frank Wilcoxon came up with this test earlier than Mann and Whitney. Okay, so those from the American continent, they tend to use Mann-Whitney U test. Those from the British area tend to use Wilcoxon Rank Sum test. Okay, so that's the difference. Why Wilcoxon Rank Sum test or why Mann-Whitney U test? SPSS is a software designed by Americans. So inside SPSS, they use the Mann-Whitney U test. Yeah? So that's the difference. That's a cultural difference. Just take note of that. So why am I using Frank Wilcoxon? I think Frank Wilcoxon deserves the honor. He's the guy who came up with the papers first about this. All right. So how it is done? Simple. How? Because basically they just arrange the data from the smallest to the largest. That's the key point. From the smallest to the largest, not the other way around. Okay, these are everything. I'm not going to worry about this. These are all the assumptions. So what we do, we assign the ranks 1, 2, 3. So the smallest value get the rank of 1. Okay, then you sum up the ranks for each group. For the example, I have a very small data set. These are between taxi drivers and bus drivers. Okay, there are only how many? 1, 2, 3, only 8 of them. Okay. So we have the taxi drivers and bus drivers. We have the glucose level. Doctor, the glucose level looks weird. This was in the milligram per deciliter. The study was done way back in 1992. At that time, they still don't have international unit. They're still using the milligram per deciliter. Okay, so we have these values 124, 141, 93.6, 139, 104. So, okay, if you, like for us nowadays, it's millimole per liter. Is much lower. Yeah? For example, my blood glucose should be around 5.8. So this one is in the old unit is milligram per deciliter. Okay, let's look at the analysis. Let's not worry about that. Haha, tak jalan. Okay, so we arrange the data in ascending order from the smallest to the largest. So smallest of 93.6, the largest is 141. So we just arrange the data set. Okay. After you arrange the data set, you just give the rank. So the smallest get the rank of 1, the largest get a rank of 8. Why? Because there are 8 data set. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, what is a smaller group? The smaller group is the, I think this is one is bus driver. So the bus driver, there's only 3 of them. So the rank of the sum of the rank is 1 plus 6, 7. 7 plus 8 is 15. Okay, 7 plus 8 is 15. Okay, so you can see here 1 plus 6 plus 8 equals to 15. This is a smaller group. So now we have to convert the sum of the rank, from t value to become p value. For that, we need to refer to the table. The table looks like this. So you can see here the value 3 and 5. Value 3 and 5. So they say it is only significant if the value is 6 or smaller or 21 or larger. The values are the t value is significant only if it is 6 or smaller, 21 or larger. But we got 15, so 15 is somewhere in between. So it is not significant. It is not, so therefore P is larger than 0.05. So there is no difference of the glucose level between the bus driver and taxi driver. Okay. So what do we do? Okay, if you conclude, it's like that. Simple. It is simple, which is null hypothesis not rejected. So how to present? You will present the median of the values between the two groups. Okay, you present the values of the two groups. All right. So if you run the SPSS, okay, it'll be under analyze non-parametric. Analyze non-parametric. You get these results. It looks like this. Okay, it looks like this. So the same as you can see. Remember we had the rank of 15. So this one is the mean rank. So 15 means 5 times 3, that's 15. Okay, so this is the mean rank. So the sum of ranks is this one, 15. So this is also how we get the p-value, and the p-value, as mentioned just now, down there is larger than 0.05, which is the value of the p is 0.8786. Okay. Okay. Therefore, it is not significant. So the problem with non-parametric test, it is very hard to get significant because you must get all the data in certain order. They must all be lumped into one end or the other. So the only way for the result to be significant is for all the data of the smallest group to be at one end or the other. Either they are all at the top or they are all at the bottom. Like this. If they are all at the top, okay, 1, 2, 3, then they are significant. Why significant? 1 plus 2 plus 3 is 6. So as you can see, 6 significant. 6 is P smaller than 0.05. Okay, or they are all at the bottom. If they are all at the bottom, 6, 7, and 8. Okay, 6, 7, and 8. So 6, 7, and 8. 6 plus 7 is 13. 13 plus 8 is 21. As you can see from the result, 21 significant. 21 significant. Why? Because the table says 21 or larger. So what is the point I'm trying to show here? I'm trying to tell you all, if you're doing analysis using a small sample size, the only way for you to get it to become significant if the data are skewed to one end or the other. If they are distributed to one end or the other. Otherwise, very hard to get it to be significant. That is why I don't like to do non-parametric tests. Okay. The other one is, of course, because very hard to goreng lah. There's nothing to discuss. You only have the median, you have the p-value. All right. So how about if you, instead of only 2 groups, you got 3 or more? You have 3 or more, then you have to do the Kruskal-Wallis one-way ANOVA test. I repeat, you have 3 or more independent groups observation, you have to do Kruskal-Wallis one-way ANOVA test. Okay. Again, this is a non-parametric test. They use the chi-square distribution to approximate if each sample size is what we expect to be. How they use which degree of freedom to use, it is the number of group minus 1. So if you got 3 groups, then you minus 1, so then your degree of freedom is 2. C refers to number of groups. Okay. Okay, same assumption as before. They must be independent. Okay. Okay, so what's the problem? The problem is this formula. I know it looks nice, but the formula is wrong because they don't have the brackets. So in fact, they have 3 components that have to be done separately. So this is one component. Sorry. This is one component. This is another component. The one in the middle there, another component. And this is the third component. So they have to be put inside a bracket and analyzed separately before you sum up together. Okay. So here's the example. We have 3 machines. Of the 3 machines, they have different filling up time. Okay. So you had 15 staff. You get these 15 staff to fill up the 3 different machines. So you end up with 5 workers per machine. So you measure the filling time. So you can get the results like this. Okay. So all the different filling time, what happened? You have to rank them, same like what we do with the EU test or the Wilcoxon Rank Sum test. Start with the smallest, then give the rank accordingly. So 1, 2, 3, 4, 5, 6, 7, and so forth, based on the values. Okay, these are the values. You give the rank. So what do we do? We take the sum of the ranks. We take the sum of the ranks, same like what we did in EU test. We take the sum of the ranks. So this sum of the ranks, I put into the formula. As you can see, I've added the brackets there. Okay. Otherwise, you can never get the answers. So once you put in the brackets, you can see I get the value of 11.58, and this 11.58 you put into the. You look at the chi-square table for degree of freedom of 2. Chi-square table for degree of freedom of 2, the cutoff point is 5.99. So H of 11.58 is larger than 5.99. Therefore, you can conclude that the median filling time between the 3 machines is different. Okay. But of course, you cannot decide which is fastest unless you do what we call the Wilcoxon Rank Sum test 1 by 1 for machine 1 against machine 2, machine 2 against machine 3, machine 1 against machine 3. Okay. So that is how we do the Kruskal-Wallis one-way ANOVA test. Okay. Is the test available inside SPSS? Yes. When you run it using SPSS, you get answers like this. This is exactly the same output. Again, you get the sum of the rank. So you can see the sum of the rank. You have to get this one times 5, this one times 5, this one times 5. Then you can get the sum of the rank. Okay. Again, we got the same answers like what they got. They got 11.58. We also got 11.58. We do manually. We get the p-values smaller than 0.05. Here they got a p-value equals 0.003. Okay. Of course, they're using a computer. They get a much more accurate answers. We are using tables, therefore we are we get a range of values. Okay, so that's how we know that it is significantly different. Okay, so that is for the Kurosawa list example. This is the equivalent of the ANOVA. This is the non-parametric equivalent of ANOVA. And lastly, for the PET-T test, the non-parametric equivalent is Wilcoxon sign rank test. The non-parametric equivalent is the Wilcoxon sign rank test. Okay. So, example given here is the blood pressure taken at 2 different times for 36 patients. I wish I have the full table to show to you, but for that I have to give you the Excel file. But it's only some of the data set. Okay, so you can see this is the table of all the results. Okay, I'm not sure whether you can see everything or not. I got a feeling the top bar is covering everything. Okay, let's see whether I can move it. Okay, so you arrange the differences. You have a differences of positive and differences that are negative. So this is the differences. Differences is the second value minus the first value. The differences is the after minus before. So you get after minus before, these are the negative values. These are the positive values. These are the no difference. So what happens, you give them the ranks based on the absolute value. What is the meaning of absolute value? You remove the positive and negative. You give the rank based on the absolute value. Doctor, how do you get 4 for this value of 1? So you can see how many value of 1 you got. You got 1, 2, 3, 4, 5, 6, 7. Yeah, I repeat back. There are 7, 1. 1, 2, 3, 4, 5, 6, 7. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 is 28. 28 divided by 7 is 4. So that's why everybody got a rank of 4. Okay, everybody got a rank of 4. Then you put all the values of 1, you have a rank of 4. Same applies for 2. 2, you got this. How many 2 are there? There are 3. They are covering the value of 8, 9, 10. So 8, 9, 10. So 8 plus 9 plus 10 is 27. 27 divided by 3. Then you end up a value of 9. So that's why they have a rank of 9 for the number 2 and so forth. So what happens now? What is important? After you give all the ranks, you will sum up all the rank. Okay. So non-parametric is summing up all the ranks. So very easy to remember. So non-parametric test, you just sum up the ranks. You look at the smaller value. So here the smaller value is 152. Smaller value is 152. Okay. Okay. Next. Luckily, I got this thermos. Why? Because the caterer bagi air dalam beg plastik. So I brought my thermos every day so that I can pour the water from the plastic into the bottle. Okay. So now we have the value of 152. So the value of 152, you look at the table. So which table to look at? We got 36 data set. Out of 36 data set, 3 of them are difference of 0. So now you only look at the critical value of 33. Why 33? 36 minus 3. Okay. So if you look at the next table, for degree of freedom So sorry, for n of 33 and p-value of 0.05, the critical value is 171. The critical value is 171. Our value is 152. So 152 is between 171 and 151. So which means the p-value is somewhere between 0.02 and 0.05. Okay, therefore p-value is smaller than 0.05. Therefore, therefore the null hypothesis is rejected. There is a significant difference of the blood pressure measured at two different times. BP before resting is significantly higher than after resting. Okay, so you want to check your BP, always rest first for 5 minutes or 10 minutes before checking the BP. Otherwise, you end up getting it higher. And make sure the nurse that measuring your BP is not too pretty. Otherwise, the BP goes up for a different reason. All right. So, and that is the concept of Wilcoxon sign rank test. Is there a test for that inside SPSS? Yes. Click Analyze, select non-parametric, select two related data. So when you select two related data, you end up with this test, which is the Wilcoxon sign rank test. As you can see, they give you the positive ranks and negative rank, which is the same like what you got, which is 152 and 409. And they give you a p-value of 0.021. Okay, you remember back the one we got 152, 151 is for 0.02. So ours is 152, therefore it is 0.021. So it means there's a significant difference of the blood pressure before and after resting. Okay, next is the Spearman candle rank correlation. I will just go through. Remember, as I said before, everything can be done through SPSS. Okay, Spearman and candle rank is for non-parametric data. Okay, non-parametric data. Also for non-linear, you can use Spearman and candle rank correlation. Okay, this one story about Spearman. Okay, so what the value you get from Spearman, it is the row. Okay, it is the row. Okay, example given here is based on visual acuity, okay, which is an ordinal data set. And you can see how we calculate the, if we are doing for calculation here given is for glucose level and BP. And we can see the formula there. And it is complicated because they're getting the difference of the rank. It is the difference of the rank, then they square it, then they end up summing up the square, the square of the differences. We put inside the formula, and then you get the row value, and the row value is converted to become the p-value. So in short, not for you to do manually, but for you to do using SPSS. SPSS will do it for you automatically. Okay, no need to calculate manually. Okay, otherwise you have to look for the Spearman table and convert the value of the row against the p-value. And for you to become significant, your row value should be very large indeed. Okay, kena 0.5, 0.6 before it becomes significant. Okay, so what happens if you do it using SPSS? You get a result like this. So they just tell you the p-value is 0.097. Sorry, the p-value is 0.599. The row correlation is 0.097. Okay, my apologies. Okay, my mind started wandering off. So just take note. This one is the row. This one is the p-value. Okay, so that is Spearman correlation. Again, inside SPSS, you just click and you get the answer. So just take note, for non-parametric analysis, you have to use the median and quartiles. For non-parametric analysis, you should not use the mean and SD. You use the median and quartiles. If the sample is very small, maybe instead of giving the median and the quartiles, maybe you can just give the range of the values. All right. So otherwise, just giving the p-value, very hard to make sense. Tak tahu yang mana lagi tinggi, tak tahu yang mana lagi rendah. You do not know which group end up with a larger value. Doctor, which one to use? Personally, on my part, I prefer parametric. If your parametric, if your all the assumptions are met, then you use parametric methods. Why? At least you can do estimation, you can do confidence interval. And the more important part, if you are doing parametric method, you can do multivariate. You can do multivariance. You can do multiple linear regression. You can do multiple logistic regression. You can do GLM. You can do repeated measures. If you are doing non-parametric tak boleh. Saya ulang balik, non-parametric tak boleh proceed to multivariate analysis. Okay? I hope that's clear. Why? Because it is clearly stated under the non-parametric analysis. Sorry, it is clearly stated under the multivariate analysis, the data must be normally distributed. If you cannot do parametric analysis because the data is not normally distributed and you can only do non-parametric, therefore, automatically you are disqualified from using multiple linear regression or any of the multivariate analysis. And with that, oops, okay. Next one, which one to use? Tak sure, buat dulu. If they are the same, then you can use the parametric one. If they are different, use the non-parametric. Okay? And with that, thank you very much.
Okay, thank you very much, Prof. So we will proceed with the Q&A session. We do have 3 questions. The first question is,
Yeah, I have to mute my mic. Sorry, my apologies. I keep forgetting that. Then I cannot see my mic. Okay, up there. Okay, stop sharing. Okay, you can get it again.
Okay, so the first question is, what if we measure using the wrong test?
Okay. Okay, if we are measuring using the wrong test, then you end up with the wrong answers. Okay, but the thing is right now, it will come back to your supervisor. Okay, so since your supervisor has got his master's or his PhD already, so your supervisor should be able to identify that and put you on the correct path. If your supervisor is the type that don't want to answer your question, he keep answering, go back and read up. Go back and read up. So if you read up, you still don't know the answers. I have already given to you just now the last time. You should contact the statistician. The link I gave you earlier, ppukm.setmore.com. Okay, I'm just going to click on the button again. I'm going to type the answer. Okay, I tak boleh klik. Okay, I tak boleh klik, sorry. Okay, so ppukm.setmore.com. ppukm.setmore.com.
Okay, so the next question is, what if Kruskal-Wallis test shows significant statistical analysis? Is it necessary to proceed with Bonferroni procedure?
Okay, you have to understand Kruskal-Wallis is non-parametric. So when non-parametric, they don't have the Bonferroni. Bonferroni is under ANOVA. Okay, so it is under ANOVA for the parametric one. So if you Kruskal-Wallis shows significant and you want to know which group is the significant one, then you proceed with Wilcoxon Rank Sum test. Okay, you will proceed with Wilcoxon Rank Sum. So I'm just going to type there Wilcoxon Rank Sum test. Okay, not Bofferini. Bofferini is for the parametric version.
Thank you,
Right.
Prof. The next question is for the Wilcoxon Rank Sum test using blood pressure parameters, for example, would it be more appropriate to use paired t-test since PP is usually parametric?
Okay. Okay. If you look carefully now, okay, just now the example given was based on a very small sample size. Okay. And for that example, we already did the KS test, the Kolmogorov-Smirnov test. And the data was not normally distributed. That's why we proceed with non-parametric test. Okay, I did not demonstrate that one just now because for the lack of time, but in my normal class, we do the KS test first. We do the KS test. After we do the KS test, we prove that the data is not normal. Therefore, we proceed with the non-parametric test. So this one, it is because we cannot use the PET test because the data was not normal. Okay.
Okay, thank you. Our next question is, can we do a meaningful discussion of our study if after all the tests, our p-value is, let's say, 0.059? Thank you.
Okay. We tend to get this kind of scenario when the p-value was almost significant. Tend to happen when we got a very small sample size. Okay. So basically, how we can get this thing done to get a good p-value of 0.05 or less. Sometimes it is a simple matter of just extending your study a bit longer and increasing the sample size. Okay, then your p-value becomes significant because it's so little, 0.059. If your data was done using parametric analysis, you can check whether the 0.059 could be smaller by doing multivariate analysis. Okay, I repeat, this is only valid if the data is normally distributed. So you can proceed with multivariate analysis, and then the multivariate analysis, after controlling for confounders, maybe your p-value become better, or maybe it will become worse. Okay, so that is how we should proceed if your p-value is borderline. If your p-value is borderline, either you increase the sample by extending the study or by doing multivariate analysis. Okay,